Hi, everyone, and welcome to our lecture video all about kinetic molecular theory. By the end of this lecture video, you will be able to articulate the relationship between the motion of particles and the macroscopic properties of gases, and also be able to correlate a particle model to a graphical representation of the movement of gases and their properties. So let's dissect what we think kinetic molecular theory is. By now, you've heard me say, chemists weren't creative when they came up with the names of stuff. So this theory, if we understand the word kinetic, we think kinetic energy, and that's the energy related to movement. Molecular just means molecule. So this theory is going to explain how molecules are able to move. Specifically, the molecules that we're going to be talking about are gas molecules. So we're continuing our conversation about gases. So when thinking about kinetic molecular theory, there's 5 key postulates that we have to be able to identify. Some of these we've kind of already talked about without formally introducing kinetic molecular theory. The first of which is that gas atoms or particles or molecules are constantly in motion, that motion is random, and when they move in a straight line path. So gas molecules are constantly moving around. They don't have a specific direction. They move in a random direction until they collide with a wall of a container or they collide with each other, which will change their direction, but they still stick to moving in a straight line path. Next talks about those collisions. We said collisions means pressure. And when something collides, when these gas molecules or particles collide, they collide with each other or their container elastically. And an elastic collision just means that there's no energy lost due to this collision. If I have 2 gas molecules coming towards each other and they collide, they're going to bounce off of each other with the same amount of energy that they had upon collision as well. Next, we have that the volume of gas particles are negligible. In actuality, right, gas molecules, even though they're really small, they still have some sort of volume. But for us to be able to understand kinetic molecular theory, we have to be able to just say and assume that the volume of gas particles are so small that we can practically ignore them. Another key postulate is that gas particles do not exert intermolecular forces on each other. There's no attractive forces or repulsive forces that they feel towards each other. These 2 postulates, specifically 3 and 4, are going to come into play when we talk more about ideal gas behavior in an upcoming lecture. Our last postulate tells us that the average kinetic energy of the gas particles is proportional to our temperature of the gas. As I increase the temperature, we talked about the other day, my particles are going to be moving more quickly. And if my particles are moving more quickly, that means that they're going to have a higher kinetic energy. So my average over all of my gases is going to have a higher average kinetic energy if my temperature is increased. So we're able to say that as I increase my temperature, I'm also increasing my average kinetic energy, which means that temperature is directly proportional to my kinetic energy. And this is going to come into play when we talk about now how our different gas laws really are confirmed by kinetic molecular theory. So a lot of the descriptions that we talked about in class the other day about why our basic gas laws are valid utilizes a lot of the same language that we talked about already, but we didn't have proper terminology, right? Everything that we talked about the other day about how our gas laws are valid is utilizing kinetic molecular theory to articulate why these quantitative relationships actually make sense. So first, let's evaluate the relationship between temperature and pressure. The other day, we said if I increase the temperature of a system with gases in it, they move faster. If they move faster, we just identified that that means they have a higher average kinetic energy. They're moving around faster. They have a higher average kinetic energy. That ultimately means we're going to have an increased pressure. because we were just able to identify that if I increase my temperature, I increase my kinetic energy. And if I relate that to my collisions, that means we're going to have more collisions. And if I have more collisions, that ultimately means I'm increasing my pressure. Moving along, we can also talk about the volume relationship with pressure. We're able to say from a perspective of volume, if I decrease the volume, my kinetic energy doesn't necessarily change because I'm not changing my temperature, excuse me. If I decrease my volume, my kinetic energy doesn't change, but we do increase the frequency of collisions. And if I increase that frequency of collisions, that's ultimately going to mean that I increase my pressure. And that is due to the fact that we're decreasing our wall area. Lastly, we can also understand the relationship between moles of a gas and volume at a constant pressure. And we think of a balloon in this case. If I breathe more air into a balloon, the volume expands. That's our same relationship. We're able to say from a movement perspective, if I have more gases, there's going to be more collisions because there's more movement due to more moles of our gas. And ultimately, because we're going to have to keep our pressure constant, our volume is going to expand. Our volume expands to make sure that our pressure remains constant. So that's our Avogadro's law. That's looking at the relationship between our pressure, our volume, and our moles as well. And again, we have already kind of talked about this language, but now we have a more formal way to be able to say, using kinetic molecular theory, we can now describe the collisions, the movement, and the average kinetic energy of a given system as well. So to challenge you a little bit, let's go ahead. I'm going to read off a question, and then this video is going to pause, and hopefully you have a moment to try and answer this yourself. So you're asked to the question's asking, use the same reasoning that we just kind of talked about to explain the relationship between volume and temperature, i.e., aka asking, why would increasing the temperature of a gas increase the volume, making sure we utilize our key components of kinetic molecular theory towards our explanation, thinking about kinetic energy, our movement, and our collisions. So we're going to pause this video and go ahead and click next once you've come up with your own answer. Okay, hopefully you had a moment to think about this answer. And we can talk about this with respect to kinetic energy, especially when temperature is in the conversation. That's a great clue to be able to say, if I'm thinking about temperature, I'm also going to want to consider a change in kinetic energy, because as I know, as I increase my temperature, I'm increasing my kinetic energy. My particles are moving with a greater kinetic energy because they're moving faster. So as they start to collide, as these collisions start to occur more frequently and with a greater force, because looking at my relationship between temperature and volume, we say temperature is directly proportional to my volume, specifically at a constant pressure and mass. This is what we said the other day to be true. In order to make sure I maintain a constant pressure, that's why my volume expands. If I'm increasing the temperature, everything's moving around faster, collisions are happening with a greater force. In order to maintain my constant pressure, that's why my volume expands. So here we're able to use the kinetic energy perspective of kinetic molecular theory to be able to establish and answer this question. So let's talk a little bit more about how we can graphically represent speed with respect to a given system. And to do that, we use Maxwell-Boltzmann distributions. Sometimes you hear this called just Boltzmann distributions. And these types of graphs describe the distribution of different molecular speeds of gas particles. So in order to understand, before we even start to identify what the trend of our curve is here, Let's understand what's on our X and Y axes. Our X-axis is showing the speed of our molecules. Our speed is shown down here, and that's our X-axis. Speed is in units typically of meters per second. And our Y-axis is the number of molecules. So what this graph is showing is our speed of gas molecules and how frequently those gas molecules are at different speeds. So the number of molecules at different speeds is shown here in this graph. And what we're able to say that in a sample of a gas at a given temperature, our gas particles do not all have the same speed. So again, what this graph is showing right here, it's showing how many molecules of gas are moving at different speeds. Diff is different. Okay, what we see here is what we call a distribution. In a mathematical setting, this is a distribution because our number starts small, it increases, and then it starts to decrease again. This right here is called a Boltzmann distribution. Our Boltzmann distribution now is showing how we have different number of molecules moving at different speeds. The key here is that this figure is showing us one type of molecule at one given temperature. So this is showing how different oxygen molecules are moving at 300 Kelvin. At one temperature, we have a range of how quickly our oxygen gas is moving. Some particles, a fewer number of particles, are moving at a really slow speed. If we see down here, if we look at this specific speed and we say that this is like 100 meters per second, we're able to say that a really few number of oxygen molecules are moving at a slower speed. However, we get to kind of the peak up here. This peak is called our probable speed. UP means our probable speed. Our probable speed is saying that because this is the peak of our figure, that is the most number of molecules moving at that speed. There are the most amount of oxygen molecules moving at just under 400 meters per second at 300 Kelvin. Moving down, we're able to see specifically another type of speed. This speed that comes up is called our root mean square velocity. That's what our RMS stands for, our root mean square speed. And ultimately, it's a little bit beyond the scope of the class, but it's another way that we're able to calculate a given speed at a given temperature. So using this distribution, we're able to say that there are some particles that move really, really, really fast. There are some particles that move at 1,000 meters per second, but there's not that many. And the reason we know that is because if I move over to my y-axis, there's really a small number on that y-axis compared to our most probable speed, which if I move over to my y-axis is a much larger value. There's a couple different ways that we can compare and contrast molecules and our different temperatures, and that's what we're going to spend the next just couple of minutes thinking about. Okay, so thinking a little bit more about Boltzmann distributions. Our Boltzmann distributions, we can think about how temperature and molar mass influence our distributions. So here we're seeing 4 different Boltzmann distributions of our nitrogen gas at 4 different temperatures. Our lowest temperature is 100 Kelvin, which is this distribution right here. And our fastest or excuse me, our highest temperature is our widest distribution down there. So a couple things we're noting. First thing that we identify is at a lower temperature, we have a much more narrow distribution. The reason I say narrow is because this is a lot smaller than this distance right here. That's what I mean by narrow distribution. That wave is really close together. And that's specifically at a lower temperature. We're able to say at a higher temperature, we have a more broad or wide distribution. And we see that when we compare 100 Kelvin to 1,000 Kelvin. We see the 1,000 Kelvin wave become really, really, really wide. And what this means is that at a higher temperature, we have fewer molecules moving at the most probable speed, but we have more molecules of N2 moving at a faster speed. So what we're able to say at a higher temperature, we have a fewer number of particles or molecules moving at the most probable speed. Again, as a reminder, the most probable speed is our peak. So our different peaks are right here. Those are our most probable speeds. At our higher temperature, we have fewer number of particles moving at the most probable speed, but we have more particles moving really fast. And because we're at a higher temperature, that makes sense. At a higher temperature, there's going to be more molecules of N2 gas moving really, really quickly, as opposed to at 100 Kelvin, we say that there's more particles moving at the most probable speed, but fewer particles moving really, really fast. And as I start to increase my temperature, we see this broadening happen here, going from 100 to 200 to 500 to 1,000, we see broadening occur. They become wider and they become more flat as well. So this is comparing how temperature ultimately impacts the same type of molecule speed and how many or the fraction of those molecules moving at a given speed. Next, let's go ahead and compare how different size or different molar masses impact our speed as well. Here we have a trend for our different noble gases. We notice helium is the smallest noble gas. It's the smallest molar mass. Molar mass, I'm going to abbreviate as MM. It's the smallest molar mass, and xenon has the highest molar mass. Okay, so what we're noticing is that the smaller the molar mass, you're going to have a larger fraction of molecules moving really, really quickly. So we're able to say that a lower molar mass means we can have more molecules moving really quickly. As opposed to xenon, which is the highest molar mass, we have fewer molecules moving really fast, but we have a fraction of molecules moving at our most probable speed. Let's think about conceptually why that is. If we have a golf ball versus a bowling ball, golf balls are able to move faster than our bowling balls are. That's related to their mass, right? Golf balls are smaller, bowling balls are bigger. The same thing is true for gases. Heavier gas molecules move slower over an average, whereas smaller gas molecules tend to move faster over our average. So we're able to say that on average, smaller molar mass gases on average move faster. And that is it for this lecture video, and I'll see you in class. Bye, everyone.